Hi, this is a PowerPoint presentation regarding correlation. So what is correlation? Well, correlation describes relationship between two variables, and it's basically just a standardized version of covariance, such that covariance is the unstandardized version of correlation. So they're cousins. Correlation precedes many analyses as if there's no correlation, then you don't do subsequent analyses. So basically, correlation is kind of a gut check on whether or not you should proceed with subsequent analyses. So it's a numeric value ranging from -1 to 1, has three characteristics. It will tell you the direction of the relationship, whether there's a negative sign or a positive sign, the form of the relationship, and then also the strength and the consistency of the relationship. So what does that mean? Direction of the relationship. So you have a positive correlation where your scatter plot derives from your bottom left-hand corner going up to your right top corner. So as x increases, y increases. This indicates a direct relationship. So another word for positive is a direct relationship. Then there's a negative relationship, whereas x increases, y decreases. Or conversely, as x decreases, y increases. This indicates an inverse relationship. So when somebody says they have an inverse relationship, they are referring to a negative correlation coefficient value. So the form of the relationship. This is the best representation of that. So correlation is most often used to describe linear relationships, especially when you talk about Pearson's R, which is a biggie. But if you look at figure A, you have a very tight linear relationship versus figure B, which is kind of nebulous. So I don't even know if there would be a form of relationship there. And then D is kind of nebulous too. And C, you can kind of fit a line of best fit to it, which is the yellow line. Other relationships do exist, so you can have like curvilinear relationships such as, quadratic, cubic, quartic, but that's a little advanced for this discussion. So the strength of the relationship refers to the degree of consistency or strength of the relationship. So a value of R equals 1 indicates a perfect positive relationship, and a value of R equals -1 indicates a perfect negative relationship, or negative or inverse relationship. And R of 0 indicates a no relationship. So there's varying degrees within there. So like if you have an R of 0.8, I would say that was a strong positive relationship or direct relationship, meaning as x increases, y increases, versus a relationship of R equals negative 0.6. I would say that's a moderate negative relationship between two variables. So now there's also part and partial correlations. So part correlations are also known as semi-partial, and that's when you control for a third variable on one variable but not on another. So you would control for it on one of your x or y, but not x and y. So then partial refers to when we control for a third variable on both variables being correlated. So if you're correlating x and y, you control for another third variable on both. So Pearson's R correlation is the biggie. You'll hear that the most by far, and measures the degree and direction of the linear relationship between two continuous variables. So if your variables are continuous, that would be your go-to correlation. Okay. First step to do this, we calculate your sum of products. The definitional formula is here, where the sum of products equals the summation of x minus the mean sub x multiplied by the y minus the mean sub y summation, where the m's are means. And there's a more simply derived computational formula where you take the summation of x and y minus the summation of x multiplied by the summation of y divided by n. Then after you take calculate the sum of products, you calculate the Pearson's R as follows. So the sum of products over divided by the square root of the sums of squares for x multiplied the sums of squares for y. Now let's do a worked example. We have some hypothetical data here. From this we can first calculate our sums of products. The chart or the table already gives you the sum of x, the sum of y, and the sum of x multiplied by y. So you can literally just plug and chug those numbers. So you have the sum of xy is 66, and then the sum of x is 12, and then the sum of y is 20, and the n is 4, because there's 4 rows there outside of the column totals. And so 66 minus 12 multiplied by 20 divided by 4, so 66 minus 60 will give you a sums of products of 6. Now, some hypothetical data. After you've calculated you can calculate your sums of products, you can calculate your R, where the sums of product is divided by the square root of the sums of square for x multiplied by the sums of square for y. And so all we now need to do that is the sums of square for x and y. R squared, also known as the coefficient of determination, measures the variability in one variable that can be determined by its relationship in another variable. Basically saying what amount of the variability in one variable can be explained by another variable. So you'll hear this most often referred to as a percentage, the R squared value. So if you have an R squared value of 0.33, they'll say, oh, 33% of the variability in y is explained by variable x. So R and R squared have a very explicit and clear relationship. So an R value of 0.80 corresponds to an R squared value of 0.64. You literally just square it. And in this way, an R squared value of 0.64 translates to 64% of the variability in y can be explained by x. So hypotesting with R. At times you do want to test the level of statistical significance of your correlations. You can do this by hypothesis testing. You can have it be non-directional or directional. Rho, the Greek letter rho, which is that cursive looking P, is referred to as the population parameter for correlation. So you're testing whether or not your R value equates to a population parameter of rho equals 0. And you'll see that a lot in hypothesis testing, that they'll refer to the Greek letter as indicating the population, so meaning you're testing your sample to the population to see if it's generalizable. So in ANOVA you'll see mu as mean, meaning the population parameter for mean. So if you have the H sub O of rho equals 0, let's say there is no population correlation, and then the alternative would be rho does not equal 0, which suggests there is some sort of correlation, real correlation. It's not 0. And then of course you can have impose a directionality on it. Alternatives to Pearson's R. There's actually a lot. This table is taken from another book, Lomax and Schumacher's Introduction to Structural Equation Modeling, or Beginner's Guide, to Structural Equation Modeling. And it just helps you kind of think conceptually about when you can use certain types of correlations. So like the Pearson's product moment correlation, the Pearson's R, you use that when both variables are at the interval level at least. So it can be ratio obvious too, but continuous basically. And then the Pearson's rank, or the Kendall's tau, you use when both variables are ordinal. So if both variables are ordinal, you would then use a Spearman's rank or Kendall's tau. Then the phi coefficient, when both variables are nominal, which you would get into when you do a chi-square analysis. Then a point by serial is where when one variable is at least interval, and another variable is dichotomous. The perfect example of this is a t-test, because your dependent variable is continuous or interval, and your independent variable is dichotomous. So point biserial right there. And then there's a couple others which you probably won't get into, but they're good to know. So Spearman correlation is referred to as R sub S, just for future knowledge, and it's for ordinal variables. And pretty much the same calculation. It's Pearson's R, except that you rank your variables and then calculate a Pearson's R. But it's pretty much the same exact thing. One thing you should be aware of is ranking tied scores. When you sometimes you will have tied scores, like in this example, you have 2 scores of 3 and 3 scores of 6. And when that happens, one way to handle it is to take the mean of the rank of those numbers. So, in the example of this example, you have 2, 3 scores, and their rank position is 1, 2, and so you take the mean of 1 and 2 as their rank to be run to calculate it, to use in your calculation of the Spearman R. So, and then for when you have 3 scores of 6, you would take the positions of 4, 5, and 6 and take the mean of that, which is 5, and therefore you have basically addressed how the influence of tie scores by taking the mean of the ranks and calculating the Spearman R. So after basically ranking original values, you can use the simplified formula, where R sub S, or R Spearman, equals 1 minus 6 multiplied by the summation of D squared over N multiplied by N squared minus 1 in parentheses. Now the D refers to the difference between the X and Y rank for each individual. So this is a simple difference score. Then we also have point biserial, which makes a lot of sense when you think of a t-test where you have one dichotomous and one continuous variable. And you can calculate that pretty simply if you have your t-statistic already. So R squared would equal t squared over t squared plus degrees of freedom. So if you've already run your t-test,